Hi everyone, Dr. P here, and in this video we're going to take a look at real gases. Now, we've seen the ideal gas law, which of course is PV equals nRT. So let's go ahead and plot PV over nRT versus pressure at temperature equal to 200 Kelvin. Now, why are we doing this? Well, 0, let's do 1.0, 2.0. Since PV equals nRT, if I divide both sides by nRT, I end up with PV over nRT. But I have 1 on this side. So this number should equal 1. So an ideal gas should have PV over nRT equal to 1 at all pressures. So we have pressure in atmosphere, and then PV over nRT. Pressure in atmospheres on the x-axis, and then PV over nRT on the y-axis, and that's unitless. And the thing is, we don't see this actual type of behavior. Instead, we will see behavior like this. So hydrogen gas shows a deviation like so. So as we increase the pressure, the value of PV over nRT gets larger than 1. For nitrogen, we get this interesting behavior where there's an initial dip, and then it gets larger. And we see some similar behavior with methane, and then lastly CO2. So this is a little weird. Let's focus in just on nitrogen. So clearly the identity of the gas actually does matter. So we'll focus just on nitrogen. And let's look at PV over nRT versus pressure for N2. So we'll make the same kind of plot here, where we'll have pressure in atmospheres on our x-axis, and then we'll have PV over nRT on the y-axis. Okay, and of course our ideal behavior would just be PV over nRT equals 1 at all temperatures. But what we actually see instead is that at low temperature, we get quite a bit of a deviation. And then as we move up to higher temperatures, we get less of a deviation. So what we can say is that a real gas is closest to ideal behavior at low pressure, so we're close to the zero pressure here, and high temperature. So lower pressure and higher temperature, we are at closer to ideal behavior. So, oops, my pen has run out here. Let me grab another one. Actually, I'm going to have to switch to blue. So low pressure and high temperature. Now, if we think about kinetic molecular theory, this makes a kind of sense, because what were our assumptions in kinetic molecular theory, or what are our ideal gas assumptions? One is that the particles occupy no volume. And we need to account for interparticle forces. Because again, we're assuming that the particles exert no forces on each other, and yet clearly we can see that there must be some exertion of forces because we have different behavior for different types of real gases. All right, so what we're going to do is come up with the van der Waals, let me put that in frame a little bit better, there we go. Van der Waals real gas law, or the Van der Waals equation for real gases. We'll call it the real gas law for right now. Well, maybe I'll call it equation for real gases. And it's based on kinetic molecular theory that we're going to have to make these changes to the ideal gas law in order to account for the assumptions that we made. So let's take a look then at how we do that. The first thing that we need to do is do the volume correction. So pressure, or P prime, that'll be our observed pressure, is going to equal nRT. Normally it would be over V, but we have to subtract a small amount due to the actual volume available to a given gas molecule. So this NB here is volume of gas molecules themselves. So it's not the volume that they occupy in terms of bouncing around the container, but the actual volume of the particles. If we cooled things down and pushed all those particles into one corner of the container, it would occupy a definite volume, and so we're subtracting that from the overall volume of the container. Here, B equals an empirical constant. Empirical meaning it has to be determined by experiment. Now, we also need a correction factor for the attractive force correction. Okay, so if we have some observed pressure, that's going to equal P prime minus our attraction correction. So that's going to equal nRT over V minus NB minus our attraction correction. And that'll give us our overall observed pressure, because we will have our initial volume corrected pressure, and then we will have a correction for the attraction. So the attraction correction depends on the concentration of gas molecules. N over V, moles per volume. For large numbers, of molecules, we have to look at the concentration of an individual particle, or not an individual particle, but the chance, what we're looking at is the chance of two particles coming close to each other. Okay, it's not just due to the concentration of one, but the concentration of both. So we actually have a square relationship, N over V quantity squared. So we end up getting our observed pressure equals P prime minus A times N over V quantity squared, where A is some other empirical constant. So we get our observed pressure equals nRT over V minus NB minus, and it's minus because we've got an attractive force, minus A times N over V quantity squared. And then we rearrange this to get the van der Waals equation, which is going to be P observed plus A times N over V squared times V minus NB equals nRT. And this is the van der Waals equation. It's a, I think, a Dutch name, and so the V is pronounced like an F and the W is pronounced like a V. Van der Waals equation. Anyway, it's okay if you say van der Waals, that's fine. What we have here is pressure with a correction factor due to the attractive force. So that's our corrected pressure times a corrected volume equals nRT. So if you want, you could look up A and B in a table. And you'll see they have different values for different gases. And so you could do an actual calculation, say a stoichiometric calculation, using a real gas. It turns out that the van der Waals equation is not 100% accurate. It's a little bit better than the ideal gas law, but there are actually other ways of accounting for real gas behavior that are more accurate experimentally, but they involve much more complex correction factors and stuff like that, so we won't go into that. So take-home message, here's the van der Waals equation for real gases, and you should understand what the two correction factors represent. And then it's nice if you can be able to plug in A and B and use this as if it were the ideal gas law in doing stoichiometric calculations. All right, well that's all for now. In the meantime, stay safe out there. Bye now.